Hello everyone, welcome back to my channel Shraddha's Physics. This video is based on statistical mechanics of the core 14. Today we will see what is Wien's displacement law. In the previous class we have already discussed the Stefan-Boltzmann law. So this Stefan-Boltzmann law, it expresses the relationship between the total energy and the temperature of the black body radiation. If you could remember, this E equal to sigma T power 4. We have already discussed E equal to sigma T power 4. This law does not give the actual distribution of energy in the different part of the spectrum. So in case of Stefan-Boltzmann law, we cannot define the actual distribution of energy inside the spectrum. So this distribution, it was achieved by the Wien, who give the application of the thermodynamical principles. It provides the relation expressing the intensity of the radiation between the wavelength range lambda and lambda plus d lambda. So it means that within a certain interval, that is lambda and lambda plus d lambda, we can say that the distribution of energy can be defined by the Wien. So let us consider a spherical enclosure whose walls it reflect perfectly but diffusely, means in all possible direction, in every possible direction it could reflect. Let it be full of radiation of energy density is U at a uniform temperature T. So it has the energy density U and the temperature is T. Let the walls of the enclosure, they move outward slowly with a uniform velocity. It means that this is your spherical cavity or spherical enclosure. It is moving in the outward direction slowly with a velocity v. So the radiation inside it, it undergo a reversible adiabatic expansion. Adiabatic expansion here means there will be no exchange of energy. The temperature T of the radiation is then related to the volume V of the spherical enclosure through the equation we know. In the previous classes we have already calculated. For the adiabatic expansion, this V power 1 by 3 into T equal to constant. Now we will calculate the change in wavelength suffered by a ray on reflection as slowly moving with the walls of the enclosure. We will see. Here in this diagram you can see this AO, it is the ray of the wavelength, it has the wavelength lambda, it is incident at some angle theta. The incident angle is theta on the wall. Let a particular wave crest strike the wall at O. So it means that we are considering the spherical wall. So a wave crest strike the wall at this point O. This crest, it will be reflected along OC. So this is your incident direction and this is your reflected direction. So if we are considering that this OC equal to lambda, then as the reflected wave crest it reaches at C, then the next will reach at O. Okay. So in time t, I can say that if the first wave crest reaches at C, then the next will reaches at O point. During this time, the wall has traversed a distance, it will travel the distance OM. So how much is this distance OM? So suppose it is moving with a velocity v and we know the time we are considering is t. So now we know the distance OM will be equal to velocity equal to displacement by time, or we can write that this distance equal to velocity into time. So here we can write that this OM equal to v into t. So the path followed by the second wave crest, this second wave crest will be how much? This will be, you can see, for the second wave crest this must travel OB and d distance. So this much, this will be lambda plus d lambda. So the increase in the wavelength due to the one reflection, though in the first case it reaches at C and in the next it will reaches at O. So the total distance it will cover, that is OB and D. If we will calculate the increase in wavelength or the change in wavelength due to the one reflection, so that will be this OB plus your BN, this much, because this is already your lambda. So the change will occur at OB plus your BN, this OB plus your BN. So here you can see that in this triangle, here this angle is theta, so that this angle is also theta and this angle is also theta. Hence this side will be equal to this side. This, it means that this OB will be equal to O prime of B. So we can write that if we want to calculate the change in the wavelength due to the one reflection, that is OB plus BN, that is your OB plus BN. So we can see this is your OB plus BN. So it is similar to this OB is equivalent to O prime B plus your BN. Clear? Here you can see that this O prime B plus Bn, it can be written as, since this angle is theta and in this right angle triangle you can see that this is your perpendicular distance, this side is your O prime. So we can write it as this is equal to O prime cosine theta. We can write like this, O prime cosine theta. So this O prime is again, since this is a bisector, so this will be OM equal to MO prime. So this can be again written as twice of, I can write this as your OM cosine theta, twice of OM into cosine theta. This OM is nothing but your velocity into time, that is Vt. So this is your 2 into Vt cos theta. Otherwise we can also write, in place of t, we know t equal to lambda by c. So in place of t we can write again to be, this is your lambda by c cosine theta. Here you can see the change in wavelength will be twice of V lambda by c into cosine theta. Now to calculate the number of reflections per second, let us consider a ray, it is striking the spherical wall at suppose some angle theta. It strikes at M at some angle theta and it reflected along Mn, this is your reflecting part, and reflected along Mn, it makes an angle also theta with the normal. The distance travelled by the beam before it suffers the next reflection, that will be equal to, this is your Mn, this is your reflection part, this is your Mn. This Mn will be equal to, you can see in this triangle, this angle is your theta, this angle is your theta, and this is your perpendicular distance, this is your perpendicular. So we can write this radius is r, it means that this will be, the diameter will be twice of r. So this is 2r. Hence this Mn side will be equal to 2r cosine theta. Since cos theta equal to b by h, we can write from this triangle Mn will be equal to 2r cosine theta. So the time taken between the two successive reflection, so between the two successive reflection, if c is the velocity of light, so we can write the total distance divided by the speed of light, that is 2r cos theta by c. Since we are considering the photon, that is the moving with the velocity of light c, we can write this velocity equal to displacement by time. So we can write the distance is your 2r cos theta. Here the time equal to total distance is your 2r cos theta divided by c. So this is your 2r cos theta by c. So the number of reflection per second, that will be 1 by t, that will be equal to c by 2r cosine theta. If delta r is the increase in the radius in time delta t, then the number of reflection in this time, that will be equal to, here you can see this is 1 by t is your c by 2r cos theta into this much time, that is delta t. So that will be equal to c by 2r cos theta, again in place of delta t, time equal to your the displacement divided by your velocity, so delta r by v. So the change in wavelength in time delta t, that is delta lambda, will be equal to, we can write this as the change in wavelength in one reflection into the number of reflection in time delta t. This is your number of reflection in delta t time. So here in this place, change in wavelength in one reflection, that will be, here we have calculated in equation 2, that is 2b lambda by c into cosine theta. So the change in wavelength in one reflection is 2b lambda by c cosine theta into this number of reflection in delta time, this will be c by 2r cos theta into del r by v. Hence by cancelling this 2 cos theta and c with c, we will get finally delta lambda will be equal to lambda delta r by r. Hence, this delta lambda by lambda we can write it as delta r by r. Again we can write volume of the sphere is V equal to 4 by 3 pi r cube. So, in place of, if we will calculate the change in volume of the sphere, this change in volume of the sphere will be delta V, that will be equal to, this is your 4 by 3 pi. Again this r cube can be written as, the derivative of r cube is 3 r square into your delta r. I can write like this. Now, you can see that this delta V divided by V, if I write delta V by V, V you know 4 by 3 pi r cube. So, that will be equal to, so here if I will divide 4 by 3 pi r cube here in the right hand side. So, this 4 by 3 pi get cancelled. Again this r cube and r square, if I will cancel this r square with your r cube, so 1 r term remain. So, this will be 3 by r into delta r. Hence, delta V by V will be equal to 3 delta r divided by r. So, delta r by r will be equal to 1/3 of delta V by V. Here in equation 4 we have calculated delta lambda by lambda equal to delta r by r. So, in place of delta r by r, if I will place delta lambda by lambda, then delta lambda by lambda will be equal to 1/3 of delta V by V. Now, integrating, this will be log lambda will be equal to 1/3 of log V plus some integration constant, that is log k. So, in place of, if I will remove, if I will remove this logarithm, then I can write this lambda will be equal to, this will be V power 1 by 3 into k. Hence, this will be V power 1 by 3 equal to lambda by k. Clear? So, in case of adiabatic expansion, we have already calculated that V power 1 by 3 into t, that is your constant, that is your some constant. So, here in place of V power 1 by 3, if I will place some constant, then in place of V power 1 by, I can write this as your lambda by k, some power 1 by 3 into t as your constant. Sorry, this is your V power 1 by 3 is lambda by k. So, in place of V power 1 by 3, I have to place directly, that is lambda by k. So, this lambda by k into t, that is again your constant. So, this constant, when we will get multiply with some constant, that will be also a constant. Hence, this lambda t equal to constant. So, this is the Wien's displacement law. So, according to it, if the radiation of a particular wavelength at a certain temperature is adiabatically altered to another wavelength, the temperature changes in the inverse ratio. It means that lambda is inversely proportional to a absolute temperature T. Clear? So, this is all for today. Thank you.